Assalamualaikum and hello everyone. So this video is about the presentation of assignment mathematics for engineering technology from group 7. In this video, first of all, we will introduce our group members and then we will talk about the application of first differential equations in carbon reduction in photosynthesis. Next is the application of second order differential equations with constant coefficient implementation dynamics. And next, the application of Laplace transforms in immune response antigen antibody reactions. And the last one is the application of Laplace transforms in Planck mechanism.
So this is the members of group 7. First is Mama Abdul Aziz. Next is me, Ahmad Faris. Next is Abdul Aziz Rasik Abdi.
First of all, for the application of first order differential equation in carbon reduction photosynthesis, for the problem solving, you have to know that the differential equation is this C in bracket T over T equal to negative K C in bracket T. And the second is the initial condition, which is C in bracket 0 equal to C naught. The third one is solving the differential equations. The given equation is separable because of the differential equations. So we can separate the variable and integrate both sides. So at the end of the integrating both sides, we can get the ln Cp equal to negative Kp plus C1, where C1 is the constant with the fraction. So for Cp, we can exponentiate both sides and we can let e to the power of C1 is equal to C0 since C0 is equal to C naught. So we get the Cp is equal to C naught e to the power of negative Kp. Next, we go to the one of the example, which is the problem statement is given the initial concentration of carbon dioxide in the chloroplast at the times as C naught. Solve the first order differential equation to find the concentration of carbon dioxide at any time. So the calculation first is suppose the initial concentration of carbon dioxide is C naught is 0.1 mol per liter and the rate constant K is 0.03 second negative 1. So find the concentration of carbon dioxide after 10 seconds. So the given from the equation is C naught is equal to 0.1 mole per liters and K is equal to 0.03 second negative 1 and T is equal to 10 seconds. So second step is using the solution that we get from the past where Cp is equal to C naught e to the power of negative 8e. Next, we substitute the value of all the given information from the equations, which is at the C at the 10 seconds, C at the 10 seconds is equal to 0.1 e to the power of negative 0.03 times 10. So we can get C at the time of 10 seconds is equal to 0.1 e to the power of negative 0.3 and C at the and we solve it and C at the time of 10 seconds is approximate to 0.07408 mole per liter. So as a conclusion, the concentration of carbon dioxide after 10 seconds is approximately 0.07408 mole per liter. This demonstrates how the first order differential equation can be applied to model the rate of carbonization in photosynthesis. It's providing insights into the dynamics of this essential biological process. So I will pass to the next presenter.
Assalamualaikum warahmatullahi wabarakatuh. Next, I will present about the application of second order differential equation with constant coefficient implementation. So we need to know the step of problem solving. First, we have the differential equation, which is d squared xt of dt squared plus 3dxt of dt plus 2xt equal to 10. And the initial condition that we given is x0 equal to 1 and dx0 of dt equal to 0. First, we need to convert the homogeneous equation into the characteristic equation, which is m squared plus 3m plus 2 equal to 0. We need to find the m value. So, after we solve for m, we'll get m equal to negative 1 and m equal to negative 2. Therefore, our general solution of the homogeneous equation is x equal to c1 exponent negative t plus c2 exponent negative 2t. After solving for the general solution, for the particular solution, since the right-hand side of the differential equation is a constant, which is the value 10, we assume a particular solution of the form x pt equal to a. So we need to substitute x pt equal to 8 into the original equation. So we will get a equal to 5. So the general solution of the non-homogeneous equation will be c1 exponent negative t plus c2 exponent negative 2t plus 5. And next, we need to apply the initial condition to get particular solution. So we need to insert the value x0 equal to 1 into the equation. So we will get c1 plus c2 equal to negative 4. So, the next step, we will insert the value dx0 of dt equal to 0 into the equation dxt of dt equal to negative c1 exponent negative t minus 2c2 exponent negative 2t. So we will get negative c1 minus 2c2 equal to 0. So we need to solve the simultaneous equation. By solving the equation simultaneously, we will get from the second equation c1 equal to negative 2c2. So we need to substitute the c1 equal to negative 2c2 value into the first equation. So we will get negative 2C2 plus C2 equal to negative 4. So we will get negative C2 equal to negative 4 and eventually C2 equal to 4. After we get the C2 value, we can insert that back to the second equation, which is C1 equal to negative 2C2. So we will get C1 equal to negative 8. Therefore, C1 will be equal to negative 8 and C2 will be equal to 4. The final solution, we just need to insert the C1 and C2 value into the particular solution. So we will get xt equal to negative 8 exponent negative t plus 4 exponent negative 2t plus 5. So the problem statement here, which is given the second order differential equation that models the timing of biomass growth in a fermentation process, d squared xt of the dt squared plus 30 dxt of the dt plus 2xt equal to 0 is initial condition, x0 equal to 1 and dx0 of the dt equal to 0. Solve for xt. So suppose we want to find the biomass concentration at t equal to 5 hours. So we just need to insert the t equal to 5 value into the already equation. Xt equal to negative 8 exponent negative t plus 4 exponent negative 2t plus 5. After we insert the t value, t equal to 5 value into the equation, we will get negative 8 exponent negative 5 plus 4 exponent negative 10 and plus 5. So we're using approximate value for the exponential term, exponent negative 5 equal to 0.0267 and exponent negative then equal to 0.00000045. So we will get answer of biomass concentration xt at t equal to 5 hours will be equal to 4.94658. The conclusion, the biomass concentration of t equal to 5 hours is approximately 4.94658 units. This demonstrates how second order linear differential equation with constant coefficient can be used to model and predict the dynamics of fermentation processes in bioprocess engineering. Thank you. I will pass on to the next presenter.
Assalamualaikum everyone. Next we will be presenting about applications of Laplace transform in immune response, antigen antibody reaction. Alright, first step problem solving. dAt over dt equals negative k1 atbt. And then we put dBt over dt equals negative k1 atbt. And then given the same method, but we change the b to c. And then second, the Laplace transform. We put all three just now into the dAt over dt from A to C into Laplace transform. And then the third one, using initial condition, SAS negative A0 equal negative K1, Laplace transform AT BT. It's on the same, but change the A to B, but with the SC S equal K1 Laplace transform ATBT. This one a bit different. Then lastly for this slide, solving the equation. The system of equation involves the convolution of AT and BT. For simplicity, assume AT equal A0 in power of 10 E negative K1 T and BT equal to B exponential negative K1 T. Therefore, ATBT equals to A0 B0 exponential negative 2k 1t. Taking the Laplace transform. Laplace transform atbt equals to a0 b0 Laplace transform exponential negative 2k 1t. Then continue. Taking the Laplace transform exponential negative 2k 1t equal to 1 over s plus 2k1. Laplace transform atbt equals to a0 b0 over s plus 2k1. And then next we substitute back. So SCS equals to K1 A0 B0 over S plus 2K1. And then CS equals to K1 A0 B0 S times S plus 2K1. And then sixth step, we do inverse Laplace transform. Decompose CS using partial fraction decomposition. So it will look like CS equals to K1 A0 B0 over S plus 2k1 equals to a0 b0 over 2 1 over s minus 1 over s plus 2k1. Taking the inverse, ct equal a0 b0 over 2 1 minus exponential 2k1 t. Alright, so this is the problem statement. Given the initial conditions, A0 equals to A0, B0 equal to B0, and C0 equal to 0. Solve for the concentration of the antigen-antibody complex CT using the Laplace transform calculation. Okay, here the equations. First, given the initial concentration of antigen A0 and antibody B0 about 1 mole, and the rate constant K1 is 1 liter mole. N not equal 1, B not equal 1, and then K1 is not equal to 0, 1 meter. Using the solution, CT equal 1.1 over 2, 1 minus exponential negative 2.0 IT, so 0.1 T, sorry. And then CT equal 1 over 2, 1 minus exponential negative 0.2 T. The step, find CT at T equal 10 seconds. So C10 equal 1 over 2, 1 minus exponential negative 0.2 of, and then we put 10 there. C10 equal 1 over 2, 1 minus exponential negative 2. Using the approximation, C10 equal 1 over 2, 1 minus 0.135, and it will turn into 1 over 2, 0.x65. So it's approximately 0.43 to 5 mole. So in the end, conclusion, the concentration of antigen-antibody complex CT after 10 seconds is approximately 0.43 to 5 mole. This example demonstrates how the Laplace transform can be applied to solve and analyze the dynamic of antigen-antibody reaction in the immune response.
Now, for the last part, application of for mathematics engineering for technology in Laplace transform is in lung mechanics. Okay, the problem solving in the lung mechanics using Laplace transform is like this. So the Laplace transform will convert differential equation in the time domains into the algebraic equation in the S domain. For example, the equation of motion for a linear lung model, including compliance C, resistance R, and A newtons I, can be written as P in the term of PT, I first second derivative plus R second derivative of T and Vt over C. So applying the Laplace transform to both sides of the equation, we can get the Laplace Pt equal to I Laplace first derivative plus R Laplace second I Laplace second derivative plus R Laplace first derivative plus 1 over C Laplace Vt. So after that, we transform into the Laplace equation. We use the property of the Laplace. So we change all the Laplace after we transform. So we get Vs equal to 1 S square Vs plus Rs Vs plus 1 over C Vs. After that, we arranging and we make a factorization. We get Ps equal to 1 S square plus Rs plus 1C equal Vs because all of it has Vs. After that, we are solving for Vs. So Vs, we get Ps over 1 S square plus Rs plus 1C. Okay, this algebraic equation is the S domain. It's much easier for manipulate and solve compared to the original differential equation in the time domain. So this is the example for the lung mechanic. So given, consider a simple lung model where the respiratory system is subjected to a step change in pressure Pt equal to P initial Ut, where Ut is the unit step function with the following parameters. So it's given resistance R is 5 cm H2O as of R, and then compliance C 0.2 liter equal to cm H2O, and then I will be negligible inductance. So determine the volume Vt of the lung as a function of time. Given the given the negligible inductance, the model reduced to Pt are first derivative plus Vt over C. So we're taking the Laplace transform and we get Ps Rs Vs plus 1C over Vs, and then we input for a step Pt that in the first one input the what we get in the problem statement, that is P initial Ut the plus S. So we get Ps equal to P initial over S. So after that, we substitute Ps into the equation. So we get P initial over S equal to Rs plus 1C over Vs. Because Ps we have find it that is in the after we get the Laplace transform. After that, we solve for Vs, and then we get Vs is the P initial over S over Rs plus 1 over C. Okay, now we want to find the Vs. So the S at the bottom will be like bring it to the down and combine with Rs plus 1C, and then we get P initial over Rs square tambah plus 1 over C. After that, we rearrange and then we get Ps equal to P initial S Rs plus 1 over C in the bracket, and then using partial fraction decomposition, we get a Vs. We separate the P initial and P initial RC and the 1 over SS plus 1 RC. 1 over RC, and then we change, and then we get the Vs after the partial fraction decomposition is we get P initial C over R times 1 over S minus 1 over S plus 1 over Vc. Okay, now we taking the inverse Laplace transform. So we after we get the using the partial fraction, we inverse the Laplace transform, and then we get the Vt equal to P initial C over R 1 minus E minus 1 over Vc Ut. After we make a Laplace transform, and we just substitute the R and S in at the equation. just like in the equation, is given R is equal to 5 and C equal to 0.2. So just substitute the equation after the inverse Laplace. So we get Vt equal to P initial 0.205, 1 minus E minus 1 over 5 minus 0.2. And then we get, after we calculate, we get the answer is P initial over 25, 1 minus E minus T. Okay, for the conclusion of this method is the volume of the lung as a function of time is Vt equal P initial over 25, 1 minus E power of minus T. Okay, this solution describes how the Laplace transform simplifies the analysis and solution of a lung mechanical problem, providing a clear quantitative method to model the dynamic response of the system to a step change in pressure.